This conference will now be recorded.
Very good morning, students. Today also we'll be continuing discussions on the previous year's questions on interference of light and ions double slit experiment. Basically, these questions are from NEET and JEE papers, previous year's papers. So let us start our discussions. The first question says the resultant amplitude of a vibrating particle by superposition of two waves y1 is equal to a sine omega t plus pi by 3 and y2 is equal to a sine omega t is a square root of 2 into a 2a and square root of 3 into a. So this is the question. I hope you have understood the question. The question says that there are two waves, see given here, y1 and y2. As you see, the frequencies are same. Only thing there is a phase difference between them is pi by 3. Amplitudes also are same. Now if they superpose on a particle, the particle will vibrate with a resultant amplitude that is given here. So you have to find out the resultant amplitude. So you know, as I was discussing in the previous class, that if you have been given two waves, you can just find out the resultant wave first, like y is equal to y1 plus y2, okay, and from there you can just do the simplifications using trigonometric identities and find out the resultant intensity, resultant amplitude and hence intensity, etc. But see, that will be a bit lengthy to do that. So you know, if you remember the formula for the resultant amplitude, if you have been given two waves of different amplitude, suppose a1 and a2, then we had seen that the amplitude will be a1 square plus a2 square, square root of a1 square plus a2 square plus 2a1 into a2 and cos of phi. Phi is the phase difference. So phi is the phase difference, okay, phase difference between the superposing wave, okay, superposing waves, okay. So this is the phase difference. Now here we know the phase difference, we know the amplitudes. What else you need? So we know phase difference is pi by 3 here. Then it is done. You just put this a1 is equal to a, a2 is equal to a, so a square plus a square, and this is 2a square into cos of pi by 3. Okay, cos pi by 3 means cos 60 degree. So cos 60 degree will be half. Okay, so this part, then what we get? We get a square, so 2a square plus this c, 2 into half means a square only. Okay, 2a square, so you will get ultimately 3a square, square root of 3a square, so you get square root of 3a. So amplitude will be, resultant amplitude will be square root of 3 into a. So this is the trick you have to remember. You have to remember this formula for the resultant amplitude when two waves are superposing on each other, okay. Then you need to just know the amplitudes and phase difference between them. That will help you to find out the resultant intensity as well as resultant amplitudes, okay. So this is the answer. Option D will be the answer for this question. Now look this question. When a thin transparent plate of thickness t and refractive index mu is placed in the path of one of the two interfering waves of light, then path difference changes by. So what will be the path difference changes? Actually, see, path difference, there will be an extra path difference introduced. How to find out that extra path difference delta? Suppose that extra path difference delta will be like they say, the optical path length when the object is moving through the medium, that is given by mu into t, and the path length when it moves in the air. Okay, same thickness in the air. So suppose here t is the thickness of that medium, right? A transparent medium. So when it passes through the medium, then the optical path length will be mu into t. That minus the path length in the air is t. So same path length in the air. So this is t. So this will give you mu minus 1 into t. So this is the extra path length will be added to the path difference. Okay, this is the extra path difference which will be added or introduced. So option B will be the answer for this. Okay, next question. Due to effect of interference, floating oil layer in water is visible color. Due to observation of this event, the thickness of the oil layer should be. So I think this so far I have not discussed in the theory part, but still I'll tell you what to do. 2 mu thickness, that is the thickness of the layer, and cos of theta is equal to the bright fringe. Okay, so the condition for bright fringe in case of film, this is reflection fringe. Okay, so reflection, interference due to reflection, this I have not discussed. So this is the formula you can use it. So I think better to skip it now, because I'll just discuss this formula or this theory first, then I'll come back to this question. Anyway, if you are trying, this will be the answer. Okay, so 10 nanometer will be the order of that thickness. So anyway, I'll just discuss this theory first, then I'll go for this question. Okay, next question is, in Young's double slit experiment, two slits act as coherent sources of equal amplitude. See, two slits, when they act as coherent sources, okay, when they act as coherent sources, then they will interfere, like interference phenomenon will be seen, that is for sure. In another experiment with the same setup, the two slits are sources of equal amplitude and wavelength lambda, but not coherent. These are incoherent. Okay, so I have two setups. See, S1 and S2, these are coherent now. Coherent. Okay, having, see, coherent means they have same wavelength and same amplitude. So in this case, interference occur, we know. The second setup also has, see, two sources S1 and S2. These are not derived from the same, or maybe the same wavelength. Fine, same wavelength, but two different sources. They are illuminated by two different sources, like sodium lamp 1. Okay, sodium lamp. There are two sodium lamp 1 and sodium lamp 2. Okay, if they are illuminated by two different sources, then maybe their amplitude same, wavelengths are same, but they are not coherent because they don't have constant phase relationship. So now the question is, so these are kind of these two setups are there. Now the question is, the ratio of intensity of light at the midpoint of the screen in the first case to the second case. That means, see what will happen in the screen middle point here. So the intensity here we get first case I1, and in this case the intensity we get in the middle, that is suppose I2. So the question is, what is the ratio of these two? So this is the question. I hope you have got the question. See, I'll now answer for this. Let me answer. See, when they are interfering, you know, with the same amplitude, same amplitude, we know this a square is equal to k square is equal to amplitude. K square is equal to k a1 square plus a2 square plus 2 a1 a2 cos of phi. Now when they meet at the midpoint, the phi phase difference will be 0. So this is 0. That means, you know, what you get here is k a1 square the k1 plus a2 whole square, k a1 plus a2 whole square, right? This is what you get. So here there are amplitude, same amplitude, k into 2a whole square. That means what you get 4k square, right? So this is the intensity. So in first case, the intensity at the middle point when the phase difference is 0 will be 4. So this k a square, let us take that as I0. So we'll get actually I1 or intensity for the first case we'll get 4I0. Okay, 4I0. Now in the second case, what happens, you know, second case it will be just general illumination. They will just add up, their intensities will be adding up. Okay, added up. See I0 plus I0, so it will be 2I0 actually. Okay, this will be added up. So what will be the ratio then? So this is actually I2, because there is no interference, so their intensities will be just added up. Okay, so this is I1. So what is I1 by I1 is to I2 then 4I0 divided by 2I0. That means 2 by 1. So 1, so it will be 2:1. Okay, so this is the answer. I hope you have understood this. You can try yourself. Now, see, in white light interference nearest to the central bright fringe will have which of the following colors? So this is very interesting. Let me just tell you one thing here. When we use in Young's double slit experiment, when we use the white light source, white light source, so these slits, they will be illuminated by white light only, right? They are illuminated by white light. Okay, plane wave. Anyway, let us say like this, and then from here they will interfere. Okay, so they are, we have seen this figure. Okay, and they will interfere at some point P, Q, etc. So you know this white color, you have VIBGEO, right? VIBGEO. VIBGEO. Violet, yellow, blue, green, orange, red. So you know there are 7 colors in the 6, I think. Violet, indigo, there was indigo, VIBGEO. There will be 2 things. I think I have just written wrongly a little bit. Let me just tell you here. Violet, indigo, blue, green. Okay, let me write like this. Violet, indigo, blue, green, yellow, orange, red. So there are 7 colors. Okay, 7 colors. And you know the lambda increases in this way. So violet will have greater energy, less wavelength, and red will be the largest wavelength. Like that, the energy increasing this way. Okay. Now, when you use white light source, what you will see, suppose this is the central bright fringe. So in this central bright fringe, there will be all the colors together. So you will see a white patch over here. You will see a white patch over here at the central point. And then actually the other fringes, see, instead of getting dark and bright, we'll get different color fringe. Okay, different color fringe will get. Instead of getting just dark or bright, we'll get color fringe. Okay, we'll get color fringe. All right, but you know the position of the bright fringes. Let us take the bright fringes itself. Position of the fringes, you know how it depends, like y is equal to d lambda n d lambda by d. So this is actually the position of the fringes. Okay, position of the fringes from, say, this is y is this way from the central bright fringe, both side y varies like this, and you know this is the order of the fringe. This is the distance between the slit and the slits and the screen. This is d, and small d is actually the slit width or separation between the slits. Okay, that is d, and lambda is the wavelength we use. So look here, when you see the color fringe, there will be a natural question: which color will be just immediately after the central bright fringe or just beside the central bright fringe? So what is going to be the color here? What is the color here, here, and here? So which color will be, like, what is the sequence of the colors? Okay, whether this will be red, violet, blue, green, whatever it may be. Like you need to know which color is going to come first, then second, third, like that. See, that answer you will get from this particular expression. Okay, so suppose this, you just take 1, 2, 3, doesn't matter with this. See, lambda position, you know the displacement of the fringes or position of the different colors will depend on the wavelength of the color itself. So y is directly proportional to lambda. That means, you know, the position of the different colors will depend on their wavelength. If the wavelength is more, then they will go away from the central bright. If the wavelength is less, then they will come near to the central bright fringe. So in this case, lambda, see, this violet has the least wavelength. Okay, even sometimes you may be asked to find out which color will have the least fringe width. So fringe width also we know d lambda by d. So here also it is directly proportional. So beta as well as y, the position is directly, they are actually directly proportional to lambda only. So both fringe width, see, fringe width is directly proportional to lambda, and why? Because other things are not changing for different colors of the light. Okay, so only thing is changing is this wavelength. So we have seen that the distance from the central fringe depends on wavelength directly proportional. Okay, that is directly proportional to the wavelength, and beta is also directly proportional to the wavelength. So if the lambda is least, then beta will be least. So least thickness, least fringe width will be for violet only. Least fringe width, this will be least for violet color. Okay, and this also will be minimum. That means it will be nearby, say near, just near or nearest point. nearest fringe will be, bright fringe will be what? Nearest fringe will be actually violet only. Violet, then it goes like this: indigo, blue, green. But obviously, as you go away from the central fringe, uh, they may not be distinctly viewed, but principally this will happen. Like different colors, 7 colors will come here, according to their wavelength. Their position will be like red will have highest wavelength, so red will be at the farthest point. Okay, farthest positions from the central bright fringe. So what is my answer then? In white light interference, the nearest to the central bright fringe will have which of the following color? It must be violet. Nearest, it is said. Okay. Okay. Now let us go to the next question. So in this question, it is said that if a transparent medium of refractive index mu, let us write that 1.5, and thickness is given 2.5 into 10 to the power minus 5 meter, inserted in front of the slit of Young's double slit experiment, how much will be the shift in the interference pattern? Okay, how much will be the shift in the interference pattern? The distance between the slits are given like this. See, 0.5 mm. This is the distance between the slits. That means small d is given 5 mm. If required, we can make it 5 into 10 to the power minus 3 meter if required. And the distance between the slits and crane is given as 100 centimeter. That means 100 centimeter means 1 meter. Okay, 1 meter is given. 100 centimeter means 1 meter. I am just making all of them in SI. So what will be the shift? The shift will be actually given by, so these few formulas. Excuse me. So few formula you should remember. So for this case, we have seen that the path difference will be like extra path difference will be this one, right? Okay, so these are all fine. You can derive the formula, that is fine, but you should remember this, that this will be given as d by small d mu minus 1 into d. So this will help you to find out the shift in the interference pattern. Okay, delta y. Because you know this, right? So y is equal to n d lambda by d, right? So actually we are coming from there itself. Okay, somewhat from there. So if we put the values here, we'll get the answer. Okay, I think I don't have much space over here, so let me just erase few things. I have been given these things here. Okay, I can take from the question itself. Okay, look this delta y, that is the shift in the fringe pattern. It is given by d mu minus 1 into thickness divided by small d. Now d is given as 100 centimeter, that means 1 meter. Okay, and mu is 1.5 minus 1, and t is the thickness, that is given as 2.5 into 10 to the power minus 5 meter. Okay, and divided by 0.5 into 10 to the power minus 3 meter. Okay, this is what it is given. Yes, so this is 0.5, this is 2.5 10 to the power minus 5 divided by 3.5 into 10 to the power minus 3. So this goes off, and see here it will be 2.5 into 10 to the power minus 2. This is in meter actually. Okay, that means this is 2.5 centimeter. So here option B will be the correct answer for this case. See, these are few things which you should remember. This formula you should remember, otherwise it will take a lot of time. You can do it very quickly if you know the formula. Okay, you have been learning, you have been doing things elaborately, that is fine throughout the year, but now during this exam you should mark up few formula by heart. Okay, now in the seventh question says, in Young's double slit experiment, the fringe width, that means beta, is given as 0.2 millimeter. If the wavelength of the light is increased by 10 percentage, see this is increased by, so delta lambda plus lambda. Okay, so this delta is actually 10%. Okay, it is increased by this. Okay, and if the separation between the slits, that means small d, is increased by 10%, small d is increased by 10 percentage. Okay, so d prime will be d plus of this. Okay, this is lambda. Okay, so this is what being done. Now we have to find out what is the increase in the fringe width. Then the fringe width will be, what will be the fringe width? Increased or modified fringe width. See, beta is equal to d lambda, capital D lambda by small d. Now see, if the lambda it changes by 10 percentage, okay, changed by 10 percentage, these are actually multiplication division term, changed by 10 percentage, and also d is changed by 10%, changed by 10%. Then what is happening, the ratio is actually doesn't change. Ratio does not change here. That means the new fringe, see the new fringe will also will be equal to this only. If the ratio does not change, lambda by d, lambda by small d, if this ratio is not changing, then there is no change in the fringe width at all. So you'll get the fringe width to 0.2 millimeter itself. Okay, you don't get confused. All right, now we'll go to the next problem. In an interference experiment, third fringe is obtained at a point on the screen with a light of wavelength this. That means the third order, n is equal to third, is obtained with wavelength 700 nanometer. Now what should be the wavelength of the light in order to obtain fifth bright fringe at the same position. So in this kind of questions, when you say that second bright fringe coincide with the fifth bright fringe, lambda wavelength for one is given, you have to find out the wavelength for the other. So in such case, you know what you have to do, you have to just write this is actually constant, n1 lambda 1. Other things are say d by d, right? These are the things. So these are constant, right? So lambda n1 lambda 1 is equal to n2 lambda 2. Now you have to find out lambda 2. Just get it. n1 lambda 1 divided by n2. So n1 is given as 3, lambda 1 is given as 700, and this n2 is 5 here. So this is 0.6. This will be nanometer because this is in nanometer. So this will be 420 nanometers. See how quickly we could do. Otherwise, what you have to do, you know, the position you have to find out. So for bright fringe, you know, third bright fringe, you know, n d lambda by small d, you have to write like this. So the third will be, so this is, so third, y third will be then 3 d lambda by, let us say the wavelength, let us write as this. So d, and then fifth one you would write 5d lambda 2 by small d. So these factors are actually same. You look, just take the ratio, or yes, you can see that. You can just take the ratio, then you get the same thing. So better to remember this thing. So when some one order of order, some order is actually, some order is matching with some other order, or with the some with the different wavelength, then you can write this thing, n1 lambda 1 is equal to n2 lambda 2. Okay, so the option is this, correct. Now let us see what will be the effect of fringe width. Effect on fringe width when the distance between slits become double. See, we know fringe width beta is equal to d lambda by 2d, sorry, d lambda by d. This is for bright. Now if the distance become, okay, distance between the slits become double, that means this becomes double. So what will be the fringe with new beta prime is, see, d lambda by double means 2d, right? So this will be actually d lambda by small d into half. Okay, that means beta by 2. Beta prime will be beta by 2. Okay, so the fringe width will be actually half times. Okay, so this is what we have already discussed. The Young's double slit experiment. Young's double slit experiment for which the color fringe, oh, sir, for which color the fringe width is least. So as I said, lists will be actually, see, blue, red. We have to write with geo. Which one has greater wavelength? Greatest is this one. Then this. So what are the things given here? So least fringe width, that means the lowest wavelength we have. So what are the things you have? Red you have, blue, yellow, green. So blue actually will have, blue is green, then yellow, okay, yellow, then red. So this is having actually least wavelength. This has minimum wavelength, so the list will be of the blue. Now this question we have to solve. In Young's double slit experiment, two slits are 0.6 millimeter distance apart. That means small d is. Interference pattern is observed on a screen at a distance. That means capital D is given as 8 centimeter. Sorry, 80 centimeter. This I can write as 0.8 meter. This I can write. If I write in terms of meter, then it is 10 to the power minus 3. You have to multiply here with this. The dark fringe is observed on the screen directly opposite to the, see, you have two slits and you have screen here. When, so this is S1, S2. Dark fringe is observed on the screen directly opposite to one of the slits. So on the screen, the interference pattern is actually exactly opposite to one of the slits. Okay, so here first dark is happening. Okay, so this is the question. The first dark fringe is observed on the screen directly opposite to the one of the slits. Then you have to find out the wavelength of the light used. So how to solve this? So we need to know what is the path difference you require. Path difference. Okay, so when they're exactly opposite to each other, the path difference. See this, if this. Okay, let me just draw this also. Come here. So what will be the path difference in this case? The path difference, if the difference between the slits is d, the path difference will be actually d lambda by d 2d. Okay, d lambda by d, that is for the bright fringes. For dark fringes, there will be odd lambda. Okay, odd lambda. So this will be actually equal to d by 2. So if you do this now, see, lambda is equal to d square by d. Now, so this thing you have to remember that you are giving this. Okay, so if we put the values now, okay, this place will not be helpful. Let me go to the next page. D square by d. D square is given here 0.6 millimeter. and this capital D is given as 100 centimeter. Sorry, 80 centimeter. That means 0.8 meter. Okay. I'm sorry. This calculation we have to do that. Okay, so better to do this thing. Okay. This is okay. Let me just check. 0.6 at okay, fine. Fast dark, right? Lambda by 2. There was 2 got cancelled. 8 centimeter, no? 0.8 meter. And what was that? 0.6 millimeter. 10 to the minus 3 would be there. 10 to the minus 3 into 10 to the minus 3. This is what it is. Okay. Alright, I think I'll just redo the calculation. There was a massive part here. Point 0.6 into 0.6 divided by 0.8. Here it will be 10 to the minus 6 as well. So this you just remove. Point 3. So 9 0.9. Okay, 0.9 area. This is 10 to the minus 6. Nanometer we have to bring, right? Nanometer we can bring. This is meter anyway. Okay, anyway, the calculation doesn't matter much. So you can do it as well at your home. Okay, do it at home. So, but this thing, you look what we have done here. Lambda is equal to it will be okay. So this 90 nanometer kind of that. Okay. All right, we'll check this once again. I think maybe in the next class there was option given this fine 80 centimeter this is centimilli 10 to the power so and okay, yeah, things are all right. Okay, we'll just cross check this answer in the next session. Cross check. Okay, so we'll stop it here for today. Next day we'll start with the diffraction pattern, the diffraction part, and the doubts we had, or the part we had just left today, that is the reflection, interference pattern due to reflection, and this question we will just discuss, and then we will go to the diffraction. Okay, diffraction of light we'll discuss. Okay, so thank you for your presence. Bye for today.